Welcome to the lecture. We will now start discussing the principle of covariance in special relativity and invariance of action, and then we will start discussing point particle action in detail. Let's begin. The principle of covariance in special relativity tells us that all the laws of physics, or rather the equation of motion governing the dynamics of the physical systems, must take identical forms in any inertial reference. So suppose working in a inertial reference frame S, the lab frame, and the dynamical equations or equation motions are typically given by some PQ rank tensors in the following way. T some PQ rank tensors, it will sum in this is up and down, and this is equal to 0. This is the generic form of the equation of motion that we know from our various examples from physics. And suppose we go to the another inertial frame S prime, let's say the rest frame of the particle, then T will be some T prime EQ, and we know that how this T prime will come from T by multiplying with appropriate Lorentz transformation or the inverse Lorentz transformations. This will have some lambda and lambda inverse, right? And we know that these tensors transform homogeneously under the Lorentz transformation. So if this T is equal to 0, so this will definitely imply that T prime will also be 0 in the S prime frame, and hence it says that the equation of motion takes the identical form in any inertial reference frame, and basically it is a consequence of the fact that they are represented by some tensors of which transforms homogeneously under Lorentz transformation according to the indices. Now the next question is, how do we get this equation of motion? So what we do in physics is that we start from an action which we take a Lorentz scalar, vary this action, and this gives the equation. Okay. This is what you have done in many times in many different contexts, like in classical mechanics, electrodynamics, and so on. Use the list action principle to derive the equation. The question is, why we take the action to be a scale, or rather a real scale? So the answer actually doesn't lie in the classical realm, and I believe the answer lies in the quantum realm. Because in quantum realm, in quantum mechanics, teaches us that a to the power I times the action gives you the probability amplitude associated with the process. And we know that probability is a scalar. It cannot change when you change from one inertial frame to another. Hence, it guarantees that action has to be a scalar. Or rather the Lorentz scale. Okay. Now, keeping this in mind, we further demand that it satisfies some other physical requirement, and let us list them off. And we will use these requirements to construct action for various cases that we'll discuss next. So what are the requirements? First one is obviously I is a scalar. under Lorentz transformation. So it remains invariant not only under the Lorentz transformations as well as under translations. So in general, it remains invariant under the Poincare transformations. Remember, Lorentz transformations, we are basically focusing on the proper orthogonal Lorentz transformation, that is boosts and rotations. And then if you consider translation, this gives the Poincare transformation. Under Lorentz transformation plus translation. Now, this I must be real. Why? Again, if e to the power I pi, e to the power I times small I times capital I, the action gives you the probability amplitude, then we know from quantum mechanics to respect unitarity, it has to be real. If it has a complex part, then unitarity will die. And then we demand that it involves at best two derivatives. This will ensure that the equation of motion that you will derive by using the variation principle from this action will only be a second order differential equation. And this is to make sure that we don't encounter any problem regarding causality or instabilities. Remember the Ostrogorski's theorem from classical mechanics. Also, this I by H has to be dimensionless. So in the unit where we set H bar to 1, which we call natural unit, I has to dimension. Okay. And also I has to be invariant under any other internal symmetry. Which do not involve transforming the space-time coordinates. So there is one more criteria which is important, but it will not be relevant for our immediate discussion, but for the sake of completeness, I'm going to write it down here. So if you're dealing with quantum field, or rather any field theories, classical or quantum, so the Lagrangian density, which we do not buy this Cardi L, should also be local. The Lagrangian density. So we'll discuss the tensor fields a bit later. And typically in field theories, this is a natural condition that we impose. Okay. Now, keeping in mind, let's try to construct some action. So the first thing that we will do to consider the case of free point particle. So now we know that a point particle traces a one-dimensional curve in the space-time. Let's say some curve. We call this as a world line. So if your coordinates are collectively written as x mu, they are function of this lambda. So lambda is a real parameter which actually defines this trajectory, and we call this world line parameter. Okay. So now all the point on this world line, a function of this lambda, which we denoted here, right? Now, what is the action for this free point particle, let's say of the mass m? So now there is a natural candidate is there for this case. Okay. What is that? So remember that the length between 2 points world line is a frame invariant, and that's the candidate for that. So again, remember that the infinitesimal square line element for Minkowski space-time given by this, which is nothing but eta mu nu dx mu, and if we break into the time and the spatial part, we have okay. So this is a invariant square interval, and if you take a square root of it with the appropriate sign, it gives you the length or infinitesimal length, right? So now for the point particle moving on this world line, so this x will be all these coordinates x0, which is c times t, and the three spatial coordinate x1, x2, x2, all will be a function of lambda, basically. So in general, this ds will be a function of this lambda, the world line parameter. So we write down the action for the point particle. I substitute Cp for point particle, a function of the coordinate, which are basically function of the lambda, is proportional to the invariant length. Now you can consider any two arbitrary points, let's say A and B, not necessarily separated by a infinitesimal distance, but they can have finite distance. So you have to integrate over entire pathway from A to B. Give the length between the two. Any two points which is separated by a finite distance. Now let's try to fix this constant alpha. How do you do that? So let's keep in mind all the criteria for the action that we have just written down before. So we demand that this action in the unit of h bar equal to 1 has to be dimensionless. So now the square root of d square is dimension of L. So if I has to be dimensionless, so alpha must be of the dimension of 1 over L. And what is the natural quantity associated with the point particle, which has dimension L? Is the reciprocal of the Compton wavelength, right? Reciprocal of the Compton wavelength in the unit of h bar 1, nothing but m times c, mass of one particle times speed of light. So alpha must be proportional to this m times c. Now still there is this kappa which we have to determine. And how do we do so? Remember, kappa is dimension there. It's already a dimension of inverse length, which will balance this dimension. Now kappa has to be dimensionless. So how do we determine kappa? Oh, we can take the non-relativistic limit. Relativistic limit, which says that all the velocity is much less than c. And we know that in that limit of our Newtonian mechanics, we know that or Lagrangian, corresponding Lagrangian mechanics, we know that this action has to be half mv square, and that will fix the kappa to -1. So please do that exercise explicitly to check what I have written is correct. So finally, we have the point particle action function of x, which are in turn function of the world length parameter, nothing but minus c. Remember the logic that we are developing to write down this action and fixing all these coefficients will be very important in all our subsequent discussions. So please keep this in mind. Now let's rewrite this in a bit more convenient way. First of all, remember that if you have to determine the equation of motion, you have to vary this action delta I. This gives the equation of motion. This is what we call principle of disk action or stationary action. And for point particle action is nothing but literally the distance between the 2 points. So you are minimizing the distance between 2 points. So we are finding the shortest distance. Also, one point we note that we have written is minus ds square and then square root of. Remember that the distance between any 2 points on the trajectory of a point particle of mass m is time lag separated. So ds square is negative. So the square root only gives a meaningful answer if you define it by minus ds square and then take the square. That will give you the real number. Action has to be real, that we do. Let's write the ds square the following way. So we know dx mu function of lambda now, because these are on the wall line, and you can write it like that, d lambda square mu lambda x mu. We just use the chain rule, and then lambda minus mc lambda square root of mu lambda. And what is this x dot? X dot mu is defined as this derivative of x mu with respect to lambda. Okay. Now we will shortly see that there is a freedom of choosing this one-line parameter lambda. We will argue that why we can do so. So at this point, you can choose lambda to be anything. So let's choose lambda to be the coordinate time or the t itself. Okay. So later we will choose it to be something called a proper time, which is much more relevant for all our subsequent discussion. But let's choose this for this at this point to be t. Now, if we do that, then we can see that dx0 t is nothing. X0 is c times t, so dx0 c. And for the other free spatial coordinate, it gives you the component of the left frame velocity v. Then we can calculate these. So this is just a matter of simple algebra. You will see that lambda equal to ds square will be nothing but gt square minus c square plus e naught square. Right. So minus sign comes because of when you raise and lower the zeroth index, there will be a minus sign. Eta 0, 0 is minus. Right. So now IPP function of this minus mc square integral of dt yes, a square, which would be in general function of time. So v is dx dt. Now you can take the non-relativistic limit where mod of v very less than c square, and you will see that in the non-relativistic limit, it will has to be integral of gt half mv square plus some term which is independent of x, and that will be cross check. So take realistic limit. Okay. Now let's discuss how we'll find the equation of them. So for that we have to vary the action. and set the first order variation part to 0, that will give you the Euler-Lagrange equation, right? So remember that we have to calculate x lambda plus some delta x small variation. Then you can tell or expand it, which will give you lambda plus you have to do some integration by parts, with some boundary term, and then you will have some thing which is proportional to delta x mu dot something. I'm writing it very schematically, and you have some stuff which is delta x square, and then you have to set the difference between these two to 0, which will make these two 0, and that gives you the Euler-Lagrange. So for the point particle case, the Lagrangian takes the following form. It has x mu lambda, which is nothing but minus m and there will be some factor of c. We can set later on that to 1. Let's keep it here. Okay. And then the Euler-Lagrange equation. You can derive it. Remember, x mu's are the generalized coordinate here. X dot mu's are the generalized velocities. The equation of motion or Lagrange equation, just x dot with respect to the generalized velocity and dt lambda. If you choose lambda equal to t, then you have ddt, but in general you can choose anything. I'm just writing is that lambda, Walden parameter, is equal to del L del x mu. You should be able to derive this equation from the first principle, which we leave it as an exercise for you to do that. Now we know that for the point particle case, this is 0 because the L does not involve any x mu's explicitly. Only it has the canonical momenta, which we will denote as L x mu, and this gives m x dot mu let's say alpha x dot. So this finally we have del L lambda x dot mu and f x dot mu x dot mu equal to 0. So we can introduce now the relativistic definition of word velocity. We'll have a relativistic definition for velocity, which is given by mu c times mu minus alpha. Okay. And then you can neatly write down the equation of motion. Del lambda So we'll stop here. In the next lecture, we will start from here and analyze this equation of, and also see if we choose different lambda, that is the different thing for these wall line parameters, how this equation of motion will look like in these different choices. Thank you for listening. We'll end it.